Good afternoon, everyone. Welcome to the seminar. I'm Dave Tilbrook from the Department of Fundamental and Theoretical Physics at ANU, and I'm hosting the series of ongoing seminars on behalf of the Australian Institute of Physics. All of these talks, the ones we have given in the past and today's talk, will be uploaded to the AIP YouTube channel. So if you've missed any previous talks, or if you want to hear Joerg's talk again, you'll be able to log in there in a couple of days and you'll be able to see it. If you're interested in theoretical physics and would like to be kept up to date with developments relating to theoretical physics, then a good way to do that is to consider becoming a member of the theoretical physics group at the AIP. It's very easy to do. Just log into the membership portal of your AIP website and you'll see theoretical physics group name under the topical groups, and you can in your membership profile section, and you can just join up there. Today's talk is by Professor Joerg Frauendiener, sorry, I knew I would get that wrong, from the University of Otago. We were just talking about the problem of English speakers speaking, correctly pronouncing foreign languages, and it is a problem. Joerg holds the position there of Chair of Applied Mathematics after obtaining his PhD in theoretical physics at the University of Tübingen, held positions at Pittsburgh, Munich, Oxford, and Potsdam before moving to New Zealand. Joerg is a Fellow of the Royal Society of New Zealand. His research interests include gravitational waves, conformal field equations, and asymptotic structure, and initial boundary value problems for Einstein field equations, and he's published widely in those fields amongst in those topics, amongst many others. As you would have seen from his abstract, the approach that Joerg is discussing in his talk today is to deal with scattering of gravitational waves by considering the relationship between asymptotic initial and final states identified with past and future light-like infinities, which, of course, in turn, rely on the conformal structure of the particular space-time under consideration. So today's talk proves to be extremely interesting. I've been looking forward to it, and deals with how conformal methods can be used to describe the scattering of gravitational waves. If you have any questions that arise during the talk that you'd like to ask Joerg, please just go ahead and type them in the Q&A panel at the bottom of the Zoom window, and we'll discuss them in detail at the end of the talk. So it's a great opportunity for me to introduce Joerg with his talk entitled "The Scattering of Gravitational Waves, a Geometric Perspective." Thanks, Joerg.
Thanks, David. Thanks very much for the introduction. And thank you for inviting me to give a seminar in this series. I think this is a great idea to have these sort of more global seminars and available basically at any time. And I think this is great. I just want to say again what David said, that if you have any questions, you can also simply interrupt me, and we can discuss anything also while I go along. Okay, so the topic that I want to talk about is scattering of gravitational waves, and my perspective is coming from a geometry point of view, and so I will try to convince you that this is something that is of interest. So, okay, let's start with scattering. We all know that scattering was introduced more or less as an experimental method by Ernest Rutherford in the early 1900s, and he received the Nobel Prize in Chemistry for his scattering experiments with alpha particles, and because this basically was the foundation of the atomic model of the of matter. And the experiments that he did was that he smashed alpha particles onto gold atoms and observed the essentially the effects of the gold atoms on the alpha particles by detecting whatever got through the gold foils, and so by observing the deflections, he deduced information about the interaction, and that gave him then the idea about the structure of the atoms. That, you know, the matter is distributed in atoms, and which consist of a nucleus and electrons that are surrounding it. So the idea is that you take particles and you smash them together, you see what happens, and from the outcome of this smashing, you try to get information about what causes the interaction between, or what the interaction between those particles is like. This is essentially also what's happening at CERN, where you're smashing protons together, and by observing the debris of these collisions, you hope you get information about the fundamental theory that governs the elementary particles. And in this way, the Higgs boson was discovered, but nothing else, unfortunately. And so it's still a problem with the fundamental theory of particles. So the question then becomes, if you can do this with all kinds of particles, can you do this with the gravitational interaction particle, or the particle that gives the gravitational interaction, the graviton? And if you can do this, then would it be of any interest? And so I cannot say much about would it be interesting, apart from the fact that it would be interesting to see whether you can do it. I have no idea what the outcome would be, except that one has some expectations that if you take a lot of gravitons and smash them together, you get black holes out of it. But that's all I can say at this stage. So gravitational waves is obviously a consequence of the theory of relativity, and this is due to Albert Einstein, who received the Nobel Prize in 1921, not for the theory of GR, but for the photo effect. He got his Nobel Prize in physics, and so gravitational waves is one consequence of general relativity. A couple of words about the theory of relativity. So the theory of general relativity is the theory that describes the gravitational interaction. It describes one force of the four fundamental forces, and it describes this force in a completely different way than all the other forces. GR is a geometric theory, whereas all the other forces are described by a Young-Mills theory, which lives on a flat space-time. And so the problem of quantum gravity is to mix those two or merge those two theories together, which is something that is, I think, still very far away. The fundamental axiom of GR, and the reason why you can think of it as a geometrical theory, is the equivalence principle, which essentially says that all particles are accelerated in the same way in a gravitational field, and once you accept that, then it's an easy step to say that, well, then the force that is the gravitational force can be incorporated as a geometrical thing. And that leads to a completely new interpretation of what the space-time continuum is, namely in the theory, it's described as mathematically a pseudo-Riemannian manifold, which we always think of as being as smooth as possible. That's an assumption that's not necessarily true, and will certainly not be true in the quantum context. But for us at the moment, that's a good enough approximation. This pseudo-Riemannian manifold is in general not a flat manifold, so it's not like an Euclidean space or anything like that. The curvature of this manifold is determined by what's in the manifold, what's in the space-time, and that's the mass distribution. And so the mass distribution, in a sense, determines the curvature. But once you have a curved manifold, you can look at geodesics, that's curves that describe the straightest lines in that manifold. And the one consequence of the Einstein equations, or the theory of GR, is that bodies move at least at the lowest approximation on geodesics. And so you have this quote by Wheeler, which says that mass tells spacetime how to curve, and the spacetime tells mass how to move. So this is a give and take between mass and curvature. Now, when you take a small mass like a pen or something, and you wiggle this pen in your fingers, then this is a change of the quadrupole moment of that system in time, and that's the reason for gravitational waves. So change of a quadrupole moment in time is the source of a gravitational wave, in the sense that this is a disturbance of the curvature around around your mass distribution, and this propagates away from the source with the speed of light. Obviously, we do not see these gravitational waves generated by pens, and that is because gravitational waves have a very low power. If you take a ruler, a yardstick or something, then it's easy to see that the power of the gravitational wave that you can send out of this using, a usual sort of frequency and so on, is 10 to the minus 53 watts. So that is not that's not a lot. The reason is that the space-time can be thought of as being a very, very stiff elastic material. Very stiff because the disturbance in that material propagates with the speed of light, and so it also takes a lot of force and power to actually excite this very stiff material. So that's why you get this low power in the gravitational waves. And so in order to create sizable gravitational waves with a sizable power, you need large bodies with huge masses at very high speeds. And that's something that exists essentially only in the universe and not on Earth directly. And so the sources for gravitational waves at the moment are huge astrophysical events, like the supernova explosion, or the merger of two black holes or neutron stars, and so on. So we are reliant on the violent astrophysical events in order to actually see the gravitational waves. So in this case, I just showed you two pictures of the Crab Nebula, what it looks like in the optical window and what it looks like in the X-ray window. This is a supernova that created a neutron star, and the other source that I talked about already is the collision of compact objects. So that's the sources from which we actually detect gravitational waves nowadays. We detect them with the gravitational wave detectors that are distributed around the Earth. That's currently, I think, 4. They all look roughly like this. This is a sort of L-shaped object which has an arm length of 3 or 4 kilometers, depending on which one you're looking at. The effect of a gravitational wave on Earth is that it changes essentially the arm length of these detectors in a very precise and characteristic way. But the change in the length, or the relative change in the length, is, as I have written here, is of the order of 10 to the minus 22. So the change in length divided by the length is 10 to the minus 22, which is, when you think about it, it's something like the diameter of an atom compared to the distance between Sun and Saturn. So you need very sensitive detectors, and the most sensitive ones at the moment are laser interferometers, and that's an image of one of those laser interferometers. That's one of the LIGO detectors. That's the one in Livingston in Louisiana. There's another one in Hanford in Oregon, and it's a detector of the same size. Yeah, that's the other detector here. And so we have those LIGO detectors. Then we have a detector in Italy. It's called Virgo, and then there is a detector in Japan, Kagra, and that's it for the moment. There are other detectors planned, but that's it. There is a small one in Germany, which is the prototype where all these things were developed. But this has an arm length of only 600 meters. That's why it's called Geo 600. But it is online and detects with the other ones, but it's not nearly as sensitive as the big ones. So usually one only hears about the big detectors. There is a planned new sort of detector, which is called LISA. That's supposed to be a detector that operates as 3 satellites that are following the Earth in an orbit around the Sun, and it is supposed to be launched in around 2035 to 38, I believe, and it will detect gravitational waves with a completely different frequency band, and so one expects to see different sources from what one currently sees. And the sensitivity is obviously also being much higher. Okay, so on to the scattering of gravitational waves. So can we scatter gravitational waves? Well, we can try, and we can see whether one can see something of it. So the questions that one needs to consider is that, when you smash gravitational waves, you expect that, because the theory is nonlinear, that these gravitational waves interact in a nonlinear way. And because this is perturbations in the curvature, you can ask what happens to the space-time structure if there is a violent collision of gravitational waves. And that is something that one obviously cannot do in the lab at the moment, but you can do mathematical investigations, and that was done years ago by Kahn and Penrose. That was in the late 1960s, I believe, and by Sekeres shortly after, where they came up with exact solutions that describe 2 plane-fronted waves, gravitational waves that are colliding head-on. And they showed that under the assumptions that they made, you will always get a destruction of the space-time curvature or the space-time structure. So in the sense that you will always get curvature singularities. Together with a then master student, Chris Stevens, I looked at a numerical setup for this situation where we construct numerically plane-fronted waves that collide head-on, and looked at all kinds of different scenarios. And in every case, we found that there are curvature singularities. So that, I should say, this is under very strong symmetry assumptions. And we know that when you make strong symmetry assumptions, you do not really capture the generic case. So what I can say is that in this restricted case, the appearance of curvature singularities seems to be the usual case. And it did not matter whether it was a high amplitude or a low amplitude. It just took longer for the waves, the singularities to appear. Okay, so that's essentially what one would expect, that if you have gravitational waves that are colliding, then you would think that if you have a large enough amplitude, that means that if the waves have a large enough energy, then you would destroy the space-time. Okay, so how do we in physics describe scattering? Well, the usual way of describing this in mechanics or quantum mechanics is that you try to map initial states to final states, and this mapping gives you information about the interaction between these two states, or between the particles that that you put in initially. So you map initial states to final states. It's called this mapping is called the S matrix in quantum mechanics. It's a matrix, or it's a map that maps the Hilbert spaces in an isometric way. And the assumption is that you can actually isolate the states into initial states and final states. So you need some sort of asymptotic conditions when the particles are non-interacting. So that means that they are far apart, and that in the past they are far apart, and in the future they are also far apart. So essentially it's a limit that involves t going to infinity or minus infinity, and the particles being spread out. So this means time goes to infinity and space also goes to infinity. And that's something that one should keep in mind when one discusses the scattering of the gravitational waves. So if we look at here, I have the situation for the Klein-Gordon equation, where we have the dispersion relation, which is omega squared minus k dot k is m squared, where m is the mass of the particle that you want to describe with your Klein-Gordon equation. If you take a mass 0, which would be the case for a graviton, or like it is for a photon, then you would get this dispersion relation, and this is an equation that in relativity describes light-like directions. So that's directions which correspond to particles traveling with the speed of light. And so geometrically then, or relativistically, this means that the initial states come in from the infinite past along light-like directions, and the final states move outwards to the infinite future along light-like directions. And the interaction, if we're talking about gravitons, is due to the space-time curvature. And that means that there is no interaction when there is no space-time curvature, and that means that the free states must correspond to a flat space-time region. So what we want, if we want to describe the scattering of gravitons, is we want to have a space-time which is flat in the light-like directions, both in the infinite past and in the infinite future. So we know that the vacuum spacetimes or general relativistic vacuum spacetimes are modeled by manifolds, four-dimensional manifolds that carry a Lorentz metric, a metric that has a particular signature. So it's not positive definite like a Riemannian one. It has signature -1 +++. And vacuum means that the Einstein tensor or Ricci tensor is equal to 0. So that's a part of the curvature vanishes. Another part of the curvature is not necessarily 0. And we want this to be asymptotically flat in light-like past and future directions. And then obviously, because it's asymptotic conditions, this will lead to a global problem, because it's something that it addresses the entire space-time. And now this person comes in. This is Roger Penrose, who received the Nobel Prize in Physics in 2020, as you know, for his work on gravitational collapse and black hole formation. But he had a very strong influence on the development of GR in general, and in particular on his ideas about the conformal properties of space-time. And the starting point was the idea of how do you characterize a space-time that I was just describing, namely a relativistic space-time which which is flat in the asymptotic light-like and past light-like future and past directions. And so his idea was that he realized that the light-like directions are the ones that do not change when you scale the metric. So when you have a light-like direction, that means that the metric, well, the length of a vector that is light-like is equal to 0. And that does not change when you multiply this with any function. And so this is scale invariant. And so if you replace the metric that describes your spacetime with a multiple where at every point you scale it with some function, then that does not change the light-like directions. So in a sense, this scaling operation here, this conformal rescaling, ignores the scale of the spacetime, so the size, essentially, the length and the time intervals, and it only focuses on its shape, and that's in a local sense. So the local shape of the manifold, in a sense, is unchanged when you conformally rescale it. So mathematically, then, what one does is that you consider a physical metric, the metric that actually does describe the complete scales of your spacetime, but you consider this only up to arbitrary scalings. So you look at equivalence classes of metrics, which are where two metrics are equivalent if one is a multiple of the other. And this will give you an equivalence class of metrics, which is called the conformal structure of the metric of the spacetime. And the property that light-like directions are not touched by this rescaling means that they are properties of this conformal structure, and they and because the light-like directions characterize causal relationships. So what can influence what? This means that the causal relations and the wave propagation of electromagnetic and gravitational waves are not changed under this conformal rescaling. And the main idea that Penrose introduced was that you can characterize infinity as boundary points where the light rays actually end up as at the boundary, as a boundary of the physical spacetime. Just a second. So in a sense, then, infinity becomes not something that is out there. Infinity becomes a local submanifold in the conformal manifold, and it has a local structure and it has a local geometry, and you can use the usual local geometric methods in order to access the points at infinity. The consequence is that this conformal structure is fundamental for spacetimes. Penrose has developed this much further, the ideas about conformal things than simply the structure of infinity here. But for us, that's enough. So just to give you an idea, when you do this conformal rescaling for a plane, a Euclidean two-dimensional plane, you all probably know this picture here. This is called stereographic projection. You can think of your spacetime as being this plane, and then the conformally rescaled metric gives you a sphere. The idea here is that you look at the points along a straight line here in the plane, and you project each point of the plane by drawing a line from that point to the North Pole. That gives you a point on the sphere. And then you find that all the points on the straight line here give you a circle on the sphere. Points on a different line will give you a different circle. But these circles, they will intersect with the same angle as the lines here intersect. That's the property of conformality. And when you follow those lines out to infinity here, then you see that the corresponding points on the sphere all approach the North Pole. So in a sense, you can you can think of the North Pole as being attached to the points of the plane, and this attached point corresponds to infinity for all these lines in the Euclidean plane. When you look at the metrics, the Euclidean metric here on the plane and the usual metric on the sphere, then you find that these are related in the conformal sense. So the metric on the sphere is equal to some function omega squared times the metric of the plane. And this omega here has the property that it vanishes on the North Pole. So this means that you have to scale down the Euclidean metric with a function that becomes 0. So you get infinity times 0, and you get a finite metric, which is the metric of the sphere at the North Pole. So this multiplying with the conformal factor here has the effect that it squashes down the large infinity of the plane down into one single point. So this was a picture where we had Riemannian signature. That's why I only get 1 point here for all planes, for all lines. When one does a similar game for the flat Minkowski space, the 4-dimensional picture, then you get a more complicated structure of infinity, where in this situation, this is representative of the 4-dimensional Minkowski space, which can be thought of as being sitting as this sort of folded handkerchief in a cylindrical space-time. And the infinity of Minkowski space, of the flat space-time, consists of these various parts here. Can you see my cursor, by the way? So you get these.
Yeah, cursor's fine. Sorry.
Yeah. Okay. Good. So I can show things. So we get various parts of infinity having to do with which kind of lines we are considering. So we get this point I0 here. That is where all the lines that are space-like, so like the lines in the previous picture, all those end up in one point here, this I0. All the lines that correspond to time-like curves, so that is where curves where time is passing, they end up at this point if you're going towards the future, or that point if you're going towards the past. So this is past time-like infinity, this is future time-like infinity. And the light rays, that's all stretched out into these pieces here. This is this script I plus and the script I minus. And so this is usually called scry plus and scry minus. It really means script I plus and script I minus. And again, we have the property that the conformal factor that relates the two metrics, the yellow one and the red one, vanishes on these on the points of infinity. So here's another schematic picture of the same situation where now this point here has been this handkerchief here has been opened up, and then one dimension was added, and so we get this picture. And so time is moving upwards. We have the script I plus and the scry minus here. all this going around here is I0, and this point and that point here corresponds to I minus and I plus. And so when we look at the situation of scattering of gravitational waves, this piece here, this is where the infinity is the past infinity is for in the light-like directions. So we expect, or we would describe the situation in such a way that gravitational waves will enter through this piece here into the space-time, and the future states that will be gravitational waves that go out, they will come out at this upper piece here, at this upper cone, and that's the outstates, the gravitational outstates. And so a scattering process would be that we specify the outstates at scri minus, and we look at, or we look for the, sorry, we specify the in states at scri minus, and we look for the out states at scri plus. And so that is the scattering situation looked at in the geometric picture of a conformally rescaled spacetime. Now, this is a nice geometric picture that Penrose has invented and that we have used here in order to describe the scattering. But if we really want to make use of this, we have to say, how do these gravitational waves that come in, how do they actually interact? And what is the end state of what's coming out? At the moment, we cannot measure this because we do not have any control about how we specify gravitational waves at any instant of time, let alone at infinity. And we do not really know how to measure gravitational waves apart from the strong ones that we actually can see. And so at the moment, we have to do this all analytically and numerically. And in order to make sense of this geometric picture, you need to establish, at least mathematically, you have to establish that there are solutions of the Einstein equations that actually admit a geometric picture like this. And this is where Helmut Friedrich comes in. He is well, he's retired now. He's a mathematical relativist from Hamburg in Germany and working at the Albert Einstein Institute for a long time. And he has made a lot of progress in the mathematical analytic discussion of the asymptotically flat spacetimes. So the problem that he is addressing, or that needs to be addressed, and that he has partially answered at least, is this, that we have this geometric picture of scattering for the gravitational waves. But the question is this geometric picture compatible with the Einstein equations in the sense that I mentioned earlier, namely, are there actually solutions of the Einstein equations that admit this geometric picture? And that is a question that is not that easy to answer. So the tools that you need are really to have a look at the Einstein equations, consider them as a set of partial differential equations, and then try to extract results from PDE theory such that you get, you know, the answer that you want. Now, this is not so easy because when you look at what happens with the metric, what happens with the Einstein tensor, which vanishes if you want to have a vacuum spacetime. When you look at the Einstein tensor of a conformally related metric, then you get this mess here. So if this here is the Einstein tensor of the physical metric that we know is vacuum, so it's 0, then this GAB hat here differs from the physical one by terms that have omega in the denominator. And if we want to have this geometric picture of scattering of gravitational waves, we need to have access to locations where omega vanishes. And so this means that this situation here, where we have these factors that are sitting in the denominator, that's not a good situation for a mathematician. And so this singular mess is something that needs a remedy. And what Friedrich did was that he reinterpreted these equations and used different variables in order to get a well-defined system of geometric equations for the GAB, for the conformal metric GAB hat and the conformal factor. And those equations are regular even when omega vanishes, so even at infinity. That's what's called the conformal field equations. And the imposition of these conformal field equations, that means if you have a solution of this, then this means that you get a GAB hat and an omega such that omega to the -1 times GAB hat is a vacuum metric. So the conformal field equations state the existence of a vacuum metric in the conformal class, which is given by GAB hat. So that's the contents of the conformal field equations. You can study those and consider them under the aspect of partial differential equations, and you can set up initial value problems for those in order to, get existence theorems about solutions and under various circumstances and so on. And so let's discuss this. So let me see. This here is the situation here. So that's the situation for the conformal field equations. We have a space-time. This here is supposed to be the center of the space-time, this line. And then we have past null infinity and future null infinity. I mean, scri plus and scri minus. And the conformal field equations are regular on those lines here. But they are still singular at this point that corresponds to I0. And in order to get this under control, what one can do is you can use a method called blow up, which is doing another transformation and using the full conformal geometry that is available. And then you get a little bit more generalized conformal field equations, which have the property that they are now singular at a set which has codimension 2. That's this point, this red point, and this red point. And that's that's the only locations where these equations are singular. These generalized conformal field equations are the only formulations of the Einstein equations that I'm aware of that gives you access to the full global structure of the spacetime. And that's obviously necessary for the scattering. So these points here play a role later on because there are still some singular issues there. So let me discuss briefly what has been done in the context of initial value problems for the Einstein equations and the conformal field equations. And I'll just show you what the well-posedness of various initial value problems, what kind of region in the global spacetime those cover. So the first existence proof of for the Einstein equations was given by Yvonne Choquet-Bruhat, and that's a local in time existence proof where you give initial data, initial values at some finite surface, finite in space, and then you let the system run, and Choquet-Bruhat proves that you get existence of solutions for some time. Okay, so you get a region that is roughly something like this. The next one is by Friedrich, where he for the first time used the characteristic initial value, the conformal field equations, and he gave a proof that the asymptotic characteristic initial value problem is well posed. This means that you give data at infinity, this is because of the use of conformal field equations, you can have access to infinity here, and you give initial values at a light-like surface, and then you can retrodict for a local in time. You can retrodict for some time. You find that there is a solution. You can do a similar thing where you give initial value on scry minus, a piece along here, and on an ingoing light-like surface, and then you get existence for for some time in the future. Then you can do the next thing, which is not retrodict but predict, where you give initial values again at a well, you give initial values at a surface at t equals constant surface that goes all the way out to null infinity, and then you can show existence of solutions for some time, and if your data are small enough, then you can show that you can cover the entire piece of space-time all the way up to this point I plus here. So one can show that this point actually exists and is regular, and the solution extends all the way up to here. So this is what's called a semi-global existence for solutions. Then in 1989, Christodoulou and Kleinerman published an article, or a book actually, with a proof of the the global stability of Minkowski space, this is called. And that is a proof not using the conformal field equations, where they give initial values at a space-like surface, so at t equals 0, if you want. And then they show the existence all for all times up to scry, up to null infinity. So this is also a semi-global existence proof. They do not address issues at this point here because they don't have access to infinity. Infinity in their case is always reached as a limit when the radius or the distance becomes large. Then there is some more work that looks at a characteristic initial value problem where you actually give initial data on past time like infinity. So this is really what you want to do when you want to do scattering. What these people here show is that you give data on so that's ingoing asymptotic states, if you want, and then they show that you can follow those states for some time again, but you do not see anything about the outgoing states. So what you want is something like this, that you specify the ingoing states here, and you get some proof of existence of solutions that allows you to at least for some region of scry plus to read out the out states. And that's something that has not been achieved so far. That's out of reach of the mathematical analysis using the conformal field equations or the Einstein equations. So there is no result in this area. So what can you do? You can look at numerical simulations. So let me talk a little bit about the numerical things, but not much. So I will, yeah, no, I have to do this step by step. So most of the codes that exist to solve the Einstein equations are really solving the standard Einstein equations in various formulations. These are the buzzwords that characterize the codes and have to do with what kind of system, what kind of formulation of equations you're using and so on. And so most codes do what the Choquet-Bruhat proof was about. You specify initial data on some finite hypersurface, and you get local existence in time. And that's what these codes then produce. And that's all the codes that are producing the simulations of black hole collisions and all that. That's all done with codes like that. They are very sophisticated nowadays, but as you can see here, they only cover a piece of the space-time. There are codes also that are based on characteristic surfaces, so that's light-like surfaces that are characteristic for the partial differential equations. And you can solve these characteristic initial value problems. And those also work, but you only get a region that is asymptotic, or really, you cannot fill in the space-time. This is because the characteristic surfaces tend to self-intersect, and then your code breaks down. And so that's a situation here that where you reach infinity, but you cannot cover the the inner parts. Then in 2003, a student of Friedrichs looked at the hyperboloidal initial value problem using the conformal field equations, and he covered, or he numerically recovered the analytical results. So this is exactly the same picture as for the hyperboloidal initial value problem. So this is a situation where you specify initial data all the way up to infinity, and then you evolve this, and you can, depending on the size of your data, you can get a regular point here, or you create a black hole, a singularity. So you see a horizon forming and then a singularity. Together with Chris Stevens, then a PhD student, I looked at the generalized conformal field equations, and we are still at the moment working on a situation where we give, we specify essentially initial values, and then because we now have a boundary here, we specify boundary data in the sense that we have gravitational waves coming in from that boundary, and then we look at the interaction of the gravitational waves with the initial values that we specify, which is usually a black hole situation. And we can follow this out to Scri+. So we can see out states here, but we do not see, we do not specify in states at Scri-. This is still away from Scri-. Now, if you want to do scattering, then it is essential that you really cover, you get this region here under control, because here are singular points, and you want to, because otherwise you need to specify boundary conditions here, which would not be a pure scattering problem then. So you want to specify data on Scri-, and you only want to look at data or waves that coming out at Scri+. So you need to understand what has to be done here in order to get around these red points. And there is no idea yet about how you deal with this. There is not analytically, well, analytically there are some ideas about what one would expect to be doing, but no proofs yet. And numerically, there is nothing done yet about this, except in some specialized situations that I want to talk about next. And that is that we have been, or people have been looking at simplified situations, simplified equations that show a similar behavior as the Einstein equations. So from the point of view of PDEs, these red points are critical because these points here are where the hyperbolicity of the equations break down. And that means that you enter into a region where you get analytical trouble and numerical trouble because your existence theorems break down, or the code breaks down because you get infinite propagation speeds. And so the problem is that we want to understand this region here where we take data somewhere here, including something to be done at these points, and then hoping that something comes out here, and that point does not spoil the result. So that's what I call exploring the corners. This is the situation of ingoing gravitational waves that go through the space-time and then come back out again. We see here, for example, an ingoing wave because of nonlinear interaction. This already scatters backwards and sends out gravitational waves to infinity. But the main idea that one should keep in mind is that anything that is happening here that wants to go to Scri plus must go through the physical space-time. There should not be a way around along this line here and through the through this point I0 or the blown up region here from I minus to I plus, because that would be unphysical and non-causal. And so that's something that one needs to prevent. And so you want to impose conditions that that prevent anything from propagating from this region, from Scri minus, along this line here to Scri plus, because that would be unphysical and non-causal. And the equations do allow this in a sense, and you have to prevent by imposing conditions on your data. You have to prevent this from happening. So as I said, we study equations with a similar behavior, and let me see how much I can say about this. So we look at approximate solution, the approximate behavior of solutions and their derivatives of equations that have a similar behavior, I should say. So this is equations that in a sense go under the name of zero rest mass field equations with particular spins, and we study those in the in a neighborhood of this region here. Topologically, this is a cylinder. That's why I refer to this as a cylinder. So analytically, you can do this by looking at formal power series expansions near those critical points. Numerically, you can solve the equations and you can study the behavior of the solutions and the convergence of the numerical solutions. That will give you indications about the smoothness of your solutions. And the aim of both of these analytic and numerical methods is that you want to find initial conditions for which you find smooth solutions which are not trivial. Because you can always have zero as an initial condition and as a smooth solution, and that's not what you want. So the zero rest mass field equations, I already talked about them. So this is the equations for a graviton, for a photon or a neutrino, spin 2, spin 1, spin 1/2. Several people have looked at this in various contexts. I'm not going to go into too much detail. So the one finds that generically, if you are not careful about your initial conditions, these solutions develop singularities at these red points on the cylinder. But one can prevent this from happening by choosing appropriate initial conditions. So there are ways of specifying initial conditions that develop into solutions that are regular. Now, what we have recently found is that the spin seems to play a kind of role here in the sense that when you have a boson, then you can give initial conditions such that the solution is regular in the future and in the past. When you have a fermion, apparently that's not possible. You can only specify either regularity in the future or in the past. So that's a distinction that I was not expecting, but that seems to be the case. Obviously, there is the question of what do these conditions mean? Because at the moment, it just means that certain coefficients in a formal power series expansion have to vanish. What this means physically, whether it means anything on moments or higher moments of these solutions or so, that's unknown to me, at least. Here is a more explicit example, but I think I'll skip this. Yeah. So essentially, this example is a very, very simple equation. It's just a wave equation, which is conformally invariant. And when you go through this, for this situation, you can actually specify initial conditions on scri minus, and you get a regular solution with information on scri plus. So this is a numerical situation, but at least for this situation, we have solved this global scattering problem, but it is way too early to say anything about the more general case. And I think with this, I'll, yeah, I think this is almost the end. So the point here is that we want to understand the full nonlinear Einstein equations near this asymptotic region where we have these singular points, and we need to understand the conditions that we have to impose initially in order to get regularity across this region, which is the cylinder, And so in order to solve the global scattering problem, we need to we need to compute initial data on scri minus such that these conditions on the cylinder are satisfied. It's unclear whether that is possible. We need to find appropriate gauge conditions. I haven't talked anything about gauge conditions. It's another chapter that is quite complicated. You would like to prove well-postness, mathematically prove the well-postness of these of the global initial boundary value problem, but that is something that is outside the scope of my facilities, and so I am not going to do this. Numerically, it means that we have to get a good, stable, numerically stable evolution scheme in order to make progress on this global scattering problem. So at the moment, I am at the stage where I say, well, let's see what happens, cross our fingers and then hope for the best. Maybe we can get something going. But I am not that optimistic that this will work in the near future, because there are so many pitfalls there that it takes a lot of work. So in summary, let me just say that I do think that this subject of gravitational wave is fascinating. Gravitational waves are still elusive, even though now we know that they are real. 10 years ago, I was always saying that, well, we will see them in some point, but now we have seen them. So we know that they exist, but they are still very difficult to get our hands on in all kinds of aspects. But the entire subject here I find very fascinating because it combines a lot of strands from various areas of science, theoretical physics, geometry, PDEs, and numerics, and so I hope that what I have been talking about at least conveys a little bit about the fascination of this problem. So thank you very much.
Well, thank you, Joerg. That was really very, very interesting. I see there's one question in the Q&A from Peter Price, but could you just say a little bit more on the previous slide from your summaries? You said choose numerically stable evolution scheme. Can you make any comments about what do you think that might consist of?
Yeah. So the the issue with the numerics is that you can go and hack anything into the computer that you think solves a PDE, but you have to be quite careful with that you take the numerical analysis or the results of numerical analysis into account, which means that in particular, when you're dealing with boundary conditions, you have to be very careful that you specify your boundary conditions not only in a way that they make sense mathematically, that with these boundary conditions solutions exist, but also numerically, because numerically you have to be quite careful with how you phrase the boundary conditions. And not every boundary condition is numerically stable. It will, if you're not careful, you will introduce numerical instabilities into your code, and then that will destroy it. Right. So there are issues where even when you have a mathematically well-posed problem, that numerically you can go completely wrong with this, and that's a problem that one really has to be aware of when you want to do numerical work.
And those problems already exist in the existing codes that you mentioned above.
Yes. I mean, these numerical problems that exist in all codes that do, I would say, hyperbolic equations.
Yeah. Okay. Yeah. David Wiltshire had a question, I think. David?
Yes. So this is more just a brief comment, because indeed, as Joerg says, there's a whole lot of theoretical physics and basic mathematical questions that are going on here. So I'd like to say there's actually, these are questions. As a theoretical physicist, I worked on all of the, many related things back in the 1980s. So there is a related dimension in quantum gravity, and that is data and phenomenology. And there are a lot of things that are falling into place now that we have gravitational waves, which were hinted at back then, but which we never understood because we didn't have the data. And so, as soon as you've got data, and the data is so good now, and it's increasing by an order, at least many orders of magnitude actually in the coming decade. So I think it's a really, really exciting time, and we need to bring in the data and statistics. I mean, I'm sitting here with a grad student who's doing just this sort of stuff, and I was just overseas in Oxford for 2 months and talking to people there who work on related issues. And it's just that it's such a big, quantum mechanics was not done by one person, and quantum gravity is certainly not going to be the same, but we're already seeing patterns that we would have never realized otherwise. And I think it's actually coming together, and we have I'm going to advertise we've got a public symposium here in 2 weeks' time, and there's going to be a public lecture related to this on the 1st of September, and that's actually going to involve simple analogies to illustrate statistics, with audience participation to illustrate statistics and geometry, with simple analogies. So just advertise that. So on the 1st of September, and it will be live streamed as well. Thank you.
Where will that be, David?
So this is at the University of Canterbury. So Roy Kerr, it turned black holes. So this is it's on the 60th anniversary of the publication of Roy Kerr's paper. So Roy Kerr, the Kerr black hole, turns, the publication date is the 1st of September. So that was exactly 60 years ago. And so it's at the University of Canterbury here in Christchurch in New Zealand. Roy Kerr will be in attendance, and he's giving a public lecture as well the day before, the evening before. Then we've got a symposium, so a lot of folk are coming from around New Zealand. It's a record, actually, the number of people who are coming, and it will be live streamed. So I think it's and recorded, and it's one to watch out for. So
that'll be great. In fact, just before we started, Joerg and I were talking about the fact that it would be good if we could get more interest in gravitational physics and
yes. Well, I think the thing is that such a lot of things are coming. There are so many people from other disciplines now, and we just need to communicate things in a way which will be understandable to them. And the problem is we're all very specialized. And yes. But there are, I mean, since I've been working on such things for a long, long time, I'm going to use actually analogies from archaeology and physiology, because I helped my wife do similar issues relating to statistics in her PhD.
Oh, that's interesting.
Yeah, back in the 80s, because so she actually used Stephen Hawking's computer account with his permission, because his was the only one that had the resources to do what we were doing.
Oh, very good. Okay, there's another.
David, sorry, I didn't know, David, that you are so old.
Oh, I'm 61. My wife's 65. So my clock goes at a different rate because I'm a relative.
That can't possibly be true, David.
Oh, well, it's the clock, you see. It's all a matter of relative. Whose reference frame, you see?
Yeah, David has been moving through life with a high speed, you know.
Yeah, that's right. Yeah, that's all.
Depends on your frame of reference. There's a question here from Peter Price. I think he's referring to the cylindrical model that you had of the flat.
Yes. Yeah, I read the question.
Yes. What are the actual dimensions in the triangle conformal picture? The interior is 4 dimensions, the boundary is 3 dimensions, the red singular point 0 dimensions or 2 dimensions. I'll just read that out for the benefit of people who might be.
So it's exactly what you expected is. So the interior is 4-dimensional, the boundary lines, the one with the script I are 3-dimensional, and the red dots are spheres, so they are 2-dimensional.
Okay. I think I could probably just wrap up now with the final question. You made an interesting comment at the end about the fact that the relationship that you had found between time parity and spin parity.
Yep.
And you made the interesting observation that for bosons, you could achieve regularity in the past and future, whereas for fermions, you can only achieve regularity in either the past or the future. Is that conclusion independent of the dimensionality of the space-time? For example, say you do the same calculation.
I cannot say anything about this because we have been looking at this only in the 4-dimensional context.
Yeah.
So
I'm wondering what happens if you pick a 3-dimensional space-time or a 5-dimensional space-time. Do the spin statistics relationships change?
Yeah, I do not know. I really do. I'm living insisting on living in 4 dimensions.
Yes, okay. All right. I guess we can't argue with that. Well, thank you very much, Joerg. I don't think there's any other questions. So thank you very much for a great talk. I just remind everybody that if you'd like to see the talk again, it'll be available on the YouTube in a few days' time. And thank you once again. And thank you for attending the seminar.
Thanks.